Okay, build-up counting. Now, build-up counting is sort of an approach to counting that's very similar to recursion, except that in recursion, you work backwards. In build-up counting, you solve smaller problems and then build up to the solution of a larger problem. Okay, it's more similar to induction. Okay. So, let's start with binary strings. Okay, binary strings, and Pascal's triangle. So let's begin with the 3-bit strings. 3-bit strings. There are 8 of them. 000, 001, 010, 011, 100, 101, 110, 111. So there are 8 3-bit strings. Okay? And we saw this before. In general, for n-bit strings, there are 2 to the n. But now let's look at these strings from the perspective of the number of ones they have. So let's tinker a little bit. So number of ones. Okay. And if it's a 3-bit string, then there can be either 0 ones, 1 1, 2 1, or 3 ones. There can't be 4 or more ones. There are no strings with 4 or more ones, and you have to have at least 1 1, at least 0 ones. Okay. So how many? So let's count. Well, when there are 0 ones, that means it's all of the bits are zeros, and there's only one string with all bits 0. That's the string of all zeros. Surprise, surprise. So there's one string with the string with all zeros. And similarly, when there are 3 ones, that means all the bits are 1. So there's only one such string of length 3 with all ones. Okay. But now when we talk about 1 1, there's 1, 2, 3 strings with 1 1. And when we talk about 2 1, there's 1, 2, 3 strings with 2 ones. Okay. So that's a relatively simple exercise, a little bit of tinkering. Now let's jump to full generality and think about n-bit strings. Okay, and we're interested in these strings from the perspective of how many ones do they have. Okay, and so let's think about the n-bit strings with k ones. So full generality, n bits, k ones. Okay, and we're interested in the number of such strings. Here we counted them for 3-bit strings. 3-bit strings and 0 ones, 1 1, 2 1, 3 1. Okay, so we're interested in counting, or we're interested in how many n-bit strings have k ones. Okay, and let's give this thing a name. Okay, there are 2 parameters, n and k, so let's write the 2 parameters, one above the other, and then close it in parentheses, and we have a notation. This is just a notation. It's useful when you're doing build-up counting to have a notation for the thing that you're trying to count, and this notation it sort of suggests what the parameters are that are involved. Okay, so nk, this is sometimes read n choose k. Sometimes we say the combinatorial coefficient nk, the binomial coefficient nk. There are many ways of referring to this thing, and we have this notation nk. Okay, it's the number of n-bit strings with k ones. And what we have shown here is that 3, 0, 3, when you're talking about 3-bit strings with 0 ones, that's 1, 3, 1 is 3, 3, 2 is 3, and 3, 3 is 1. So the number of 3-bit strings with 1, 1, and so on. So I give you this exercise. Compute 2, 0, compute 2, 1, and compute 2, 2. Okay, pause the video and compute these. And then also compute 1, 0 and 1, 1. Okay, so k 1-bit strings. Okay, so pause the video, 1, 2 seconds, but if you're coming back just for the ride, okay, so number of 2-bit strings with 0 ones, again, it's just 1, and it's just 1 here. And here there are 2 2-bit strings with 1, 1. 1-bit strings, there's 1 with 0 ones and 1 with 1, 1. Okay, what we observe is that, when we're interested in k equals 0, so n0, n choose 0 is always 1. And that's no surprise. You have n bits, you have a lot of bits, but you have no ones, so there's only one such string, which is all zeros. Similarly, n is equal to 1. So you have n bits and they're all 1. Okay. Analogous to the n-bit strings with k ones, we can talk about the number of n-bit strings with k zeros. Okay, and if you think about it a little, you'll see that there's no distinction between zeros and ones. If we talk about, if we're interested in the string with k ones, if you flip each string with k ones, you get a string with k zeros. So the number of strings with k zeros, okay, should equal the number of strings with k ones. So this should also equal nk. But an n-bit string with k zeros is an n-bit string with n minus k ones. Okay? And so the number of n-bit strings with k zeros is the number of n-bit strings with n minus k ones. Okay? And we know what that is. That's exactly this notation that we developed. That's n minus k. So what we have developed is an interesting identity. We have developed the identity nk is equal to n minus k. It's a sort of a symmetry relationship. And we derived this without knowing anything, about any formula for nk. This must hold just by virtue of the symmetry between zeros and ones. When we're counting strings with k ones, it's the same as counting strings with k zeros, but k zeros means n minus k ones. This is a fundamental identity. It's a symmetry identity, right? And we derived it with what's called a combinatorial argument, i.e. without knowing what this formula is. Now let's go for the jugular. Let's go for let's try to count nk. Okay. So for example, what is 6-4? 6-bit strings, 4 ones. Okay. And let's try to do this systematically. And this is where the build-up method comes in. And it's a beautiful application of the sum rule. Okay. So let's look at, nk. So n-bit strings with k ones. And we can focus on k being at least 1. So k is greater than 0 because we know what it is when k is 0 and we know what it is when k is n. So we are interested in the situation where 0 is less than k, which is less than n. So let's look at such a string with k ones. It's, b1, b2, b3, up to bn. So it's n bits, okay? And there are k ones in here. Now, there's, since k is not n and since k is not 0, there's at least 1 1 and there's at least 1 0. So all such strings either end in 0 or end in 1. Okay. So there are the strings which end in 0 and there are the strings which end in 1. Okay. And by the sum rule, the number of k-bit strings with k1s must equal the sum of these two. Must equal the sum of the ones that end in 0 plus the sum of the ones must equal the ones that end in 0 plus the ones that end in 1. Okay. Now if it ends in 0 and ultimately has k1s, there must be k1s in here. Okay. And so to get all these strings, we just take all the n minus 1 bit strings with k1s and add a 0. So there are n minus 1 k of those. N minus 1 bits, k1s, there are n minus 1 k of those. Here, we've already used up a 1. So if this whole string has to ultimately have k ones, there must be k minus 1 ones in here. So we have an n minus 1 bit string with k minus 1 ones. And then you can take any one of those and add a 1 and you get a string of this form with k ones ending in 1. Okay. And how many n minus 1 bit strings have k minus 1 ones? Well, it's just n minus 1, k minus 1. Okay. That's the beauty of introducing this notation. Okay. It allows us to talk about such quantities without knowing exactly what they are. Okay. And this guy here is nk. Okay. And by the sum rule, and this is the fundamental step in the build-up method. By the sum rule, nk is equal to n minus 1k plus n minus 1 k minus 1. That's the sum rule. Okay. Beautiful. Okay, so let's see, what have we derived? Essentially, we have derived a recursion for nk. It says that nk is related to, the same quantity, but for a smaller value of n and k, and for a smaller value of n and k minus 1. Okay. And we can use this recursion to compute nk, for example, 6-4. But like I said, if you use this recursion to compute nk, for example, if you program this and run it, and I encourage you to do so, you will see that it takes a long time to run. And so the build-up approach, i.e., sometimes this is called dynamic programming, this dynamic programming approach, but forget about the term. The build-up approach is much more efficient. And so let me show you the build-up approach. And in doing so, I'm going to derive for you Pascal's triangle, which many of you might have already seen. Okay. So fundamentally we have that nk is equal to n minus 1, k minus 1, plus n minus 1, k. So let's draw a table. On this dimension, I'm going to have n, and n can be 1, 2, 3, 4, 5, 6, 7, and so on. Okay. I'm interested in 6, 4, so I only need to go up to 6 in theory. Okay. And so, let's put the value of k here. So k can be 0, 1, 2, 3, 4, 5, 6, 7, 8, and so on. Okay. So let's draw. Since I love drawing lines, let's draw some lines. Some beautiful lines. And you can continue this table as much as you want. I'm not going to do the whole huge table. Okay, I'm just going to put some lines here. Make it easier for me to sort of fill in the table. Okay. Now, okay, remember that when n equals 1, 1, 0 and 1, 1 were both 1. Okay. What about 1, 2? Well, how many 1-bit strings have 2 1s? None of them. Because we can have at most 1, 1. So if we wanted to, we could put in zeros here. So whenever k is bigger than n, it's just trivially 0. If we wanted to, we could sort of also define that nk is 0 when k is negative, if we wanted to. Okay. Now, we saw that when k is 0, so you have 0 ones, then n0 is always 1. So we have 1 down this column of the table. And we also saw that, so n0 equals 1 and nn equals 1. So we have these two. These are in some sense base cases for the recursion. Okay. And we're just going to fill it in this table. So nn, so 2 is 1. 3 is 1. 4 is 1, 5 is 1, 6, 7, 8, and so on. So along the diagonal, we have 1. Along the first column, we have 1. Okay. Now, we're interested, for example, in 6, 4. So we're interested in this guy. Okay. Now, let's see what this recursion says. And we could implement it as a recursion. It's just inefficient. This recursion says that, nk you obtain by going to n minus 1, k minus 1. Okay, so n minus 1, k minus 1. So you go up and to the left. Okay, and n minus 1k. So you just go up in n. So you lower n by 1. So you need these two numbers, and you take the sum of those. Okay, so above and above to the left. Okay, you take the sum of those, and you get this value. Okay, now we could go backwards, but it's easier and more efficient to go forward, because look, I can immediately fill this guy in. It's the above and above left values added together. So 1 plus 1, 2, and indeed 2, 0 we saw earlier was exactly 2. Okay, so let's fill in this table, and now we can do it very rapidly. Okay, so these two sum to give 3, give 4, these two give 5, 1 plus 5, 6, 1 plus 6, 7, and so on. Okay, 2 plus 1, 3, 3 plus 3, 6, 4 plus 6, 10, 5 plus 10, 15, 21, and so on. 3 plus 1, 4, 6 plus 4, 10, 4 plus 1, 5, okay, 10 plus 10, 20, 10 plus 5, 15, 5 plus 1, 6. Okay. 20 plus, 15 plus 20, 35, 20 plus 15, 35, 21, 7, 1, and so on. You can fill out this whole table. This triangle that we're filling out is called Pascal's triangle. Okay. And if we want 6, 4, 6, 4, well, that's 15. Fantastic. So, even though we don't have a formula for nk, we have a very efficient way to compute nk using Pascal's triangle, or basically using this recursion. This recursion is sometimes called Pascal's identity. Pascal's recursion. Okay? And this is Pascal's triangle. And you might have seen Pascal's triangle before as a sort of a game. I show you the rule for filling in, I start with 1, 1, and 1 along the diagonal, and 1. So you start with a triangle that's, has a 1 on the left column and a 1 on the right column, and then this rule for filling in, you look at the 2 above and add, and you've filled in this triangle. Now I've shown you that this Pascal's triangle is related to the combinatorial coefficient, the number of n-bit strings with k1s. And we can get any particular value for nk, using Pascal's triangle. It's efficient, but it's not a formula. We'll soon get a formula, don't worry. Let's move on to goodie bags. Goodie bags and build-up counting. Goodie bags. Okay, we're going to use a similar approach. Remember, when you had 3 candies in a goodie bag, so the size equals 3, and the number of colors equals 3, then there were 10 different goodie bags. Okay, we saw this at the beginning of the lecture. And we posed the question, what if the size equals 5 and the number of colors equals 10? So that's a much more complex object. How many such goodie bags? You can think of these goodie bags with 5 candies when there are 10 colors of candy as complex objects. And we're asking you to count complex objects. And whenever you face this problem of counting complex objects, okay, and it looks daunting, think about build-up counting. Think about starting small, okay, and building up to the big guy. Okay, so we already started small. We counted size 3. okay, and number of colors 3. Okay. And the first thing we do, just like when we approach the binary strings, the n-bit strings with k1s, let's introduce a notation. And there are two parameters here, the size and the number of colors. So let's define q of n and k equals the number of, goodie bag size n goodie bags when you have k colors of candy. Okay. And so what we have here is that Q3, that's equal to 10. And we're interested in Q5, 10 equals question mark. Okay, so we're going to approach this problem in a similar way, using build-up counting. Okay, and so what we need to do is we need to think about the goodie bags of size n, and when you have k colors of candy, and try to break it down into simpler problems. So let's look at a goodie bag of size n. So you have n candies. Okay, so you have n candies, and k colors. Okay, and this number is q, n, k. Okay, good. Okay, so now we need to somehow relate this to a simpler problem. And let's imagine that one of the candy colors is red. Okay, so I'm just picking red as one of the candy colors. And I'm going to use the sum rule in the following way. And this is where the creativity in a build-up counting method comes in. So the goodie bags with n candies and k colors, well, either none of those candies are red, so no red. Okay, that's type 1. Or you have at least one red. At least one red. Okay? And by the sum rule, the total number of such goodie bags with n candies and k colors is the number that have no red candies plus the number that have at least one red candy. Okay. Now, if at least one is red, so you have one candy that's red, I'll shade it in red, okay, and then you have your remaining candies. Okay. And if your goodie bag has no red candies, then, it has no red candy, so none of these are red. Okay. Now let's think about each of these types of goodie bags. This is a goodie bag with n candies. Okay. And since it has no red, it must use only k-1 colors. Because you started off with k colors of candy, but now these are goodie bags with no red, so they must have, they are using only k-1 colors. Okay. In which case, the number of such goodie bags is q of n and k-1. Now, what about this type of goodie bag? Well, it has one red candy that we know, okay, and then there are n-1 other candies. Okay, and there can be all k colors in here. In fact, you get any n-1 candy goodie bag with k colors, and now add one more red color, okay, candy, and you have a goodie bag of this form. So these n-1 candies can use all k colors. Okay, and you take any one of those and add red, and you get a goodie bag of this form, of this type, that fits into my category of n candies with k colors. Okay, and so, since I can take any n-1 size goodie bag with k colors and add the red candy, the number of these should be equal to the number of n-1 size goodie bags with k colors. So this is going to be q of n-1 k. Now we can apply the sum rule. Q n k is equal to q n k-1 plus q n-1 k. Bam! Just like with the binary strings, okay, with the n-bit strings that have k1s, the size n goodie bags using k colors, we have a recursion. In this case, the recursion is interesting. So I'm computing q n k, and I need, q n for a smaller k, or q for a smaller n, and the same value of k. Okay. And again, we can program this as a recursion. We'll need to figure out what the base cases are. We're going to do that in a minute. Okay. But programming it as a recursion, go for it. You'll see that it'll take a long time to compute. So the build-up method is much faster. Okay. The inductive approach, the dynamic programming approach. So let's build the table just like we did for Pascal's triangle. So we are interested in, okay, so I'll put on this dimension n. So n, and I'll put on this dimension k. So n can be, so, in theory, you could have a goodie bag with 0 candies. It's kind of a trivial goodie bag. 0, 1, 2, 3, 4, 5, 6, and you could keep going. We are interested in, Q5, 10, so n is 5. Okay, and K, so the number of colors of candy can be 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, and so on. Okay, so let me do my fancy drawing. Boom, boom, boom. Okay, and then the lines. And let's see if we can do some base cases, some easy cases. Okay, when n equals 0, okay, so there are no candies in your goodie bag. It doesn't matter how many colors you have, there's just one goodie bag with 0 candies. So here we have 1, 1, 1, 1, 1, 1, 1, 1, 1, 1, 1. Think of those as base cases. Okay, what about when k equals 1? So you have just one color of candy. No matter how many candies are in the goodie bag, if you have just one color, there's just one goodie bag with all candies of that color. So this is also 1, 1, 1, 1, 1, 1. Fantastic. Now, let's see what this recursion says. For example, for Q510. So Q510, this guy. Okay, what is Q510? Well, what it says is, it says go, keep the same value of n and decrease k by 1. So go left by 1. So go left by 1. Okay. And then this guy says, keep the same value of k and go up, go reduce n by 1. So go up by 1. Okay. So take these two values, add them together, and you can get the question mark. But the problem is we don't have those two values yet, and that's where you could use a recursion to get those values, but that's slow. So let's do the build-up method, and look at how quickly the build-up method quickly fills up this table. Okay. So what this says is that you look at these two and you can get this. 2. These two gives 3. These two gives 4, 5, 6, 7, 8, 9, 10, and so on. Look, 1 plus 6, 7. Okay, now how do we get this guy? These two, 3. These two, 6. These two, 10. These two, 15. These two, 21. These two, 28. And so on. Okay, these two give me this. 4. These two give me this. 5. These two give me this. 10. These two give me this. 6. These two give me this. 15. 20. And you can continue to fill this table, and I encourage you to pause the video. I'll give you a few seconds. Continue to fill this table and tell me how many goodie bags of size 5 can you make when you have 10 colors of candy. So pause the video. 1, 2, 3, 4, 5. If you're coming back and you solved it and you got the number 2002, you're very good at build-up counting and implementing this recursion and using the build-up approach to fill in this table. Fantastic. 2002. If you didn't get 2002, either I made a mistake or you made a mistake. Okay. So that's good. That's build-up counting. I'll just mention one more problem that we talked about. Okay. So this other problem that we talked about was so in this scenario where you have, goodie bags of size 3 and 3 colors, there are 10. And then I talked about bulk packs. So bulk packs. Okay, so a bulk pack has, 5, size 3 goodie bags. Okay. So, how many bulk packs are there? Okay. So, you can think of this bulk pack. So, I leave that as an exercise for you to compute, but I'm going to give you some hints. Essentially, you can think of this bulk pack as another kind of goodie bag, a hyper goodie bag, where the candies in this goodie bag are the bags themselves. So you have 5, so you have a hyper goodie bag with 5 hyper candies. So the candies in this goodie bag are not quite candies, they are three packs of candy. Okay. And then, how many colors of these hyper candies are there? Well, there are 10 colors of these hyper candies. Okay. So, I now give you a challenge to show that there is a very, very tight relationship between the number of such bulk packs and this number 2002. And what I've done here, essentially, is built a relationship between a correspondence between bulk packs, okay, and goodie bags. And this kind of correspondence is what we're going to discuss next. Counting using a correspondence, using what's called a bijection. So let's erase and we'll be back. Bam, bam, bam.